All right. So this is a concept, lattice energy, that may or may not be on your final exam. So we just want to make a quick video over it. Um, you want to explain what lattice energy is, Rish?
So basically, right, lattice energy, the formal definition of it is the energy required to separate the ions within a crystalline structure.
Mm-hmm.
It's basically the main format of the definition.
Exactly. So, like in this little image here on the right, there's a crystalline structure. So this could be a good example of like sodium and chloride salts, right? So we know that when you pour a little one granule of table salt onto your food, it's not just one. It's not one sodium chloride, right? It's a big structure. It's a big crystal lattice of a bunch of sodium and chloride ions.
It says that the ratio of those ions would be 1-to-1. Like there's one for every one sodium ion, there's one chlorine ion.
Exactly, right? So, for determining which I guess crystals are going to have a higher lattice energy, it's important to think of the electrostatic force that keeps these ions together. And this equation right here is the definition of the electrostatic force, and it just says that it's proportional to some K, some constant, which you don't need to know. This is just the underlying principle, times the two charges. Therefore, the bigger the charges, the bigger the force of attraction. And if the force of attraction is greater, then you would have higher lattice energy. And it's inversely proportional to the radius squared. Therefore, the bigger the ions, that leads to a lower force of attraction, right? Because it's inversely proportional. A lower force of attraction due to the larger radius would result in lower lattice energy. So some examples that you would see on a final would be like this. So we would see sodium chloride, lithium chloride, potassium chloride, and then we'll do cesium chloride. All of these have the same charge, right? If we were to break these into their ions, you would get Li plus Cl minus, Cl minus for all of these, right? Na plus, K plus, Cl minus, and then cesium plus Cl minus. And you want to explain which one, how they would determine which one has the highest or lowest, or how would they would rank it, Rish?
So right, your lattice energy is basically, you look at your charges, right? So if your charges have the same magnitude as they do here, so like as you can see, there is both a +1 and a -1 for all of these. So the charges are the exact same magnitude here. You would look at your radius now. So you look at your atomic radius, right? And as you recall from periodic table, your atomic radius would increase as you go down and then also increase as you go left. So cesium, right, has your greatest atomic radius, followed by potassium, followed by sodium, and then followed by lithium. So what does that mean, right? That means that as you have a larger radius, the force of the electrostatic force will be lesser and lesser. So as the radius increases, there will be less force acting upon the molecule. So if there is less force within the molecule, it would take less energy to it would take less energy to maintain the lattice. So therefore, if you look at something like lithium, it's got a pretty small radius, and a small radius would mean that it has a greater electrostatic force. So if we look at it that way, your lithium chloride lattice would be the hardest of these to break apart. So that's why we'd say that if we were to rank these from like lowest lattice energy to the highest, we'll put cesium chloride at our number 1, taking the lowest spot, followed by our potassium, followed by our sodium, and then followed by lithium as the highest lattice energy.
Exactly. So, like he said, the way he knew he had to look at the radius here was because he realized that the charges Q1 and Q2 are the exact same for each one, right? Each one, like he said, is +1 and -1. And we know that the radius of Cl minus chloride is going to remain the same. So the only thing changing is the cation's radius. So like he said, again, to reiterate, he realized that the plus and minus charge remain the same. So in this case, there's no changing of the Q's. The only change is the radius, and as you get a larger radius, as you go from lithium to cesium, you're going to have the lowest lattice energy here, and the highest would be here. Now let's look at some other examples. So this is we can term this the radius effect, okay? So we'll abbreviate that to radius effect on lattice energy. The next thing would be the charge effect. So this is looking at things like sodium chloride versus, let's see, what else do we have? We can do lithium oxide, so Li2O. And then we can do aluminum oxide, so Al2O3. And is there anything else we can do? Maybe, you have any other ideas, Rich?
Maybe, possibly.
We can do, I'm trying to do something with the 4, but.
I don't think any of the 4 compounds
Ionic.
are ionic.
Yeah, right.
Say potassium nitrate.
Okay, so KNO3. So between these, we realize that the charges on everything here is going to, so we have to break these into their charges, right? So because right now the radius is really fluctuating, so it's easier to look at the charge effect. So sodium plus and Cl minus is broken down here. Lithium plus and then O2 minus is that one. Aluminum 3 plus and O2 minus is this one for aluminum oxide, and then K plus and NO3 minus. Okay. So again, let's keep in mind this electrostatic force equation. So Fe, electrostatic force, is equal to some constant we don't care about. It's just this is the principle that will help us solve these problems over r squared. So because there's so much fluctuation in radius, it's easier to look at the charge difference. The one that has the highest charge is going to have the highest force, electrostatic force. So therefore, if the ones with the highest electrostatic force, again, would have the highest lattice energy. So which one between all of these would have the highest? If you said aluminum oxide, you would be right, because you remember these are being multiplied in this equation. So if you were to multiply these 3, a positive 3 times a negative 2, you would get negative 6. That means the electrostatic force is multiplied by some factor of 6 for aluminum oxide, right? So let me erase that. So aluminum oxide would be ranked at the highest lattice energy, so we'll do Al2O3. Next would be the one with the second highest charges. So we know this is going to be 1 times 1, right? So it's just 1. This would be negative 2 times 1. That's 2. And this one would be 1 times 1 again. So this is 3. Or not 3. So this is 1, right? So that would, these are tied in terms of charge. But the next highest charge would be 2 times 1, which will give us 2. So Li2O would have the second highest lattice energy. And you would have to look between these two. So because the charges are the same in sodium chloride and potassium nitrate, you start looking at the atomic radius, okay? Sodium is going to have a smaller radius than potassium. And then, I'm not exactly the exact radius of a chloride ion, but I gotta imagine it would probably be lower in size than this thing here. O, that's right, plus negative 1, negative 1. Yeah, so I gotta imagine that a chloride is a much smaller than this polyatomic ion, right? So therefore, I would say this is smaller, and we know that a smaller radius would yield a bigger force, or you can say, since this one's bigger and this is inversely related, a bigger radius would yield a smaller force. So it would be KNO3 and then sodium chloride. All right. So again, that's the charge effect kind of mixed with the radius effect when you're looking between these two here. So again, the basic principle for these types of problems is looking at the ones with the highest charge are going to have the highest lattice energy. And then if you have some that are comparable in size, then you start looking at the radius, or not comparable in size, comparable, the same charge effect, then you start looking at the radius effect, okay? So usually the first thing I would do is look at the charge effect. If you're given something like this where all of them are the same and it's requiring you to use clearly the radius effect, then you would use the radius effect. But if you have some like this one where it gives you different charges, the ones with the highest charge will give you the highest lattice energy. And then if you have some that are the same charge like these two, then you have to take into account that radius effect. So yeah, if there's any questions on this concept, I hope this video helped, but if there's any other questions on this, just feel free to DM us in the group me or put it in the group me, the chat, so that way other people may have the similar questions and you can go over them. We can talk them out. All right. Have a good one. Good luck on your final exam, and see y'all tomorrow. Bye-bye. Rich wants to say bye.
All right. Bye, everyone. Have a great rest of y'all's day.
See ya.